Okay. Well, 2 minutes. That's not too bad. Yeah. I don't think this one's going to take us too long. I may or may not go through all the examples this morning because they're going to start to look a lot like the weak acid examples. Because, I mean, as you can imagine, weak bases are kind of just the opposite. So, I mean, there's a couple of things we need to talk about here, but weak bases, again, they're going to take protons away from water, okay? And what that's going to end up doing is making OH minus ions. Now, this is in general, okay? Now, again, this doesn't account for Lewis acids and bases, that sort of thing, but this works for the Bronsted-Lowry definition. So the general equation for this, now remember the general equation for acids is HA plus H2O yields H3O plus A minus, okay? So that's your general equation for acids. You can see how that's similar to the one for bases, just kind of turned around. So you've got your B, whatever it is, and it's going to take a hydrogen away from the water and then form HP plus OH minus, okay? Now sometimes this B might have a negative charge on it, this base, in which case it wouldn't have a positive charge over here, it'd just be neutral, right? So it just depends on the situation. Unfortunately, there is no shorthand way of writing bases, all right? You have to put the water in there when you write the base equation. Because it's not dissociating really, like with the acids, it's actually taking a hydrogen from water, okay? So we can't leave the water out of the equation because really that is what's happening here. And I mean, technically, again, this is really what's happening for acids too, okay? So that's the most correct way to write this, with the water in it. But with bases, you have to put water in the equation, okay? You're going to see NH3 a lot, okay? And I think on the AP packet that we have, I'm sure that NH3 pops up several times. So there's the reaction. The equilibrium constant for this reaction. I should have that in the notes. I'm going to have to just open up the book to this section so that I've got all these KBs in front of me. So ammonia is 1.8 times 10 to the negative fifth. And again, that's a number that you're probably going to become familiar with. But as you can see, this is called KB instead of Ka. Makes sense, right? Equilibrium constant for bases instead of equilibrium constant for acids. So 1.8 times 10 to the negative fifth. I feel like sometimes I go really fast through confusing things and then I stop and take too long on things that are really, really simple. I don't know what that is. All chemistry teachers tend to do that, I think. Are we good on that? All right, so again, Kb is the base dissociation constant, and that's talking about the equilibrium where a base is taking a hydrogen from water. And it's going to form OH minus and a conjugate acid. So again, a place in the book where you can, you know, read KBs if you get bored. It's kind of fun. Not really. Anyway. Okay, so calculate the concentration of OH minus in a 0.15 molar solution of NH3. Okay, and once again, you're going to start to see how similar this is to what we've been doing with bases, or with acids, which is kind of the opposite process now. So what's our equation here? We've got NH3 plus what? Yeah, I mean, we're putting it in a solution, so it's going to be with water. And then what are our products going to be here? NH4 plus, because now we have one extra hydrogen. And what's our other product? OH minus, okay? So there's our equation. Okay, and we want to know the concentration of the OH minus in a 0.15 molar solution of NH3. Now this, again, this is kind of an awkward way to ask this question. You have to understand what they want when they ask this sort of question, okay? Because again, to make a 0.15 molar solution of NH3, we're probably going to put the ammonia into the water. And we're going to figure out how much we need to put into the water in order to make a 0.15 molar solution, right? But as soon as we put that into the water, it's not going to be a 0.15 molar solution anymore exactly, because some of that is going to change into NH4 plus and OH minus, right? So when they're asking for the concentration of the OH minus, there essentially is none at the beginning. Okay, I should stop here because I keep meaning to say something and I keep forgetting. Is it true that we have no OH minus in a solution of pure water? No, we have some, right? Because we talked about the auto-ionization of water the other day, right? What is the concentration of OH minus in pure water that's completely neutral? Yeah, do you think that matters very much? Compared to the OH minus that we're going to end up getting from this base. And the same thing goes for H plus, right? We have been completely ignoring the fact that there's a little bit of H plus in this pure water before we put an acid into it. But compared to the amount of H plus that's coming from the acid, it makes no difference whatsoever. Okay, that's why we've kind of been ignoring it, and I keep forgetting to say that, but probably kind of important to notice. All right, so we've got our ice table here. And we're starting with a 0.15 molar solution of the NH3. And again, we've got none of these to begin with, we can assume, because the reaction really hasn't started yet. Okay. Now, I don't care about water because it's not in my equilibrium expression, right? So, again, this starts to look very familiar, right? We're just going to do our typical negative x plus x thing here. 0.15 minus x, x, and x. Okay. Now, do you think that we can make our simplifying assumption here? I sure hope so. Otherwise, again, we have to do a quadratic formula, right? So if it works for acids, it's probably going to work for bases. I should say if it works for weak acids, it's probably going to work for weak bases, right? So let me go ahead and write that up here. Our Kb expression for this one, I should write the number. What is the number for the NH3? Did you guys write it down? 1.8 times 10 to the negative fifth, okay. And that is equal to x squared over 0.15 minus x, but again, I'm going to just assume that 0.15 minus x, because so little of this actually does change into the NH4 and the OH minus, I'm going to assume our x is very small compared to the 0.15, okay? And we'll check our assumption at the end just to make sure that that's okay. So we've got 1.8 times 10 to the negative fifth times 0.15 gives me 2.7 times 10 to the negative sixth, and that's equal to x squared. Okay, so then we take the square root of both sides here. We end up with a concentration of our x equals 0.001626, okay. So 0.0016 or 1.6 times 10 to the negative third, however you prefer to write that. And they're asking for the concentration of the OH minus. Okay, well, the OH minus concentration just is x, so that's it. Okay, now we want to go ahead and check our simplifying assumption here. So you take the 0.0016 divided by our initial concentration, which is 0.15, multiply by 100. That's about 1.1% of our original, so we're okay to make the assumption this time, all right? So this is our OH minus concentration. All right? So again, not a lot different than what we were doing with acids. It's just bases instead. The main thing here is just knowing how to write the equation, I think. That's really the only thing that's different. Okay, which of the following compounds should produce the highest pH as a 0.05 molar solution? Pyridine, methylamine, or nitrous acid? Well, what are you going to need to know in order to be able to figure that out? Probably need to know their KBs, right? Okay, so let me tell you those. The pyridine is 1.7 times 10 to the negative ninth. I think I wrote that right, yeah. Methylamine, that KB is 4.4 times 10 to the negative fourth. And nitrous acid. What? Okay, let's just go ahead and rule that one out right off the bat, right? Because that's an acid. Is that going to have the highest pH? Probably not, okay? These other things are bases, so they're definitely going to have higher pHs than nitrous acid is going to have, because that's going to be giving H plus to the solution, not OH minus. All right, so we don't need to worry about that one. I mean, you could look up the Ka for that, but honestly, that might be a little bit confusing, because we haven't really talked about how to get from Ka to Kb yet, so let's just forget about that. You actually can do that. All right, so between the two that we have left, which one is going to have the highest pH? Okay, in other words, which one is the strongest base, right? And you can look at the Kb's here and you can tell the methylamine, it's a much stronger base, okay? Which means that if we write the equation for the methylamine, see, methylamine is NH2CH3 plus water, just to make sure that we get what's happening here. You can kind of put this hydrogen where you want. I'm not exactly sure where's the best place to put it. But that's going to be our general reaction here, right? And this this is going to happen more often than the pyridine taking a hydrogen from water and making OH minus, okay? So there will be more OH minus in the solution coming from the methylamine than there will be from the pyridine. And for that reason, because there's a higher concentration of OH minus coming from the methylamine, that's going to have the highest pH. Does that make sense? I want to make sure I'm not making any mental leaps. Okay. All right, so weak bases. There are kind of two general categories for weak bases. Now remember, we talked about strong bases. Strong bases are the ones that have OH minus in them, right? Like the sodium hydroxide, potassium hydroxide, and then some of the alkaline earth metals. Weak bases are harder to identify. Okay, that's going to be your main problem with a weak base, is even realizing that it's a base. Okay, now a lot of times they'll tell you it's a weak base, or they'll ask you to write the Kb expression for it, and that's going to give you a hint that it's a base. Okay, but some things that you can look for to identify things as bases. Okay, and actually we just did the methylamine example, so I guess I guess I could rewrite that one there. I don't really want to. Did you guys write it down from the previous page? Okay. All right. So if you have a neutral substance that has an unshared pair of electrons. Now this kind of sounds familiar. When else did we talk about unshared pairs of electrons? Okay. We did talk about it when we talked about weak acids. When else did we talk about it, like maybe earlier in the year? Unshared pairs of electrons that end up being shared with something else. Okay, we did talk about it with orbitals too. You're right. I guess we talked about it a couple of times. There's one other time I'm thinking about that specifically has to do with acids and bases. You know, the ones that have really long names and make you sound smart when you say them. Okay, let me just tell you. So what I was referring to was the coordination compounds, right? Okay, with the coordination compounds, you've got the Lewis base has this extra unshared pair of electrons, right? And it's going to share that pair of electrons with something else. Okay, that was a bad line of questioning on my part. Because you answered every single one of those questions correctly. So I was just asking bad questions. All right. Anyway, point is, nitrogen is a big, big clue. Okay, if you see a nitrogen, that is a huge clue that we're probably talking about a base here, because nitrogen typically, in the compounds that it forms, it typically will have an unshared pair of electrons. Okay, and if it has an unshared pair of electrons, then it can pull a hydrogen off of water fairly easily and make that OH minus. Okay, so methylamine again is an example of that. I guess if I drew the structural formula, well, I mean, I don't need to draw the whole structural formula for this, but just show this to you. When you make the Lewis structure for this, the nitrogen is singly bonded to the carbon, and you end up with a lone pair of electrons out here on the nitrogen. Okay? And so what that lone pair can do, that lone pair of electrons is negatively charged, right? Electrons have a negative charge. So they're going to attract the positively charged hydrogen on water. All right? And so you've got an H2O here. This one has a partial positive charge to it, right? That's going to be attracted to this lone pair of electrons, and then you end up with OH minus. Okay? So that's why if you have an unshared pair of electrons, that's really a big hint that, hey, we've got a base here. Okay? And nitrogen is very commonly it will have an unshared pair of electrons when it forms compounds. Okay? So you're kind of looking for nitrogen, honestly, when you're looking at bases. Then another thing you're looking at is anions, things that are negatively charged, okay, overall. So an example of that, you put NaClO into water, what's immediately going to happen to it? It's ionic, so it dissociates, right? It splits apart. So you're going to end up with sodium, which I really don't care about at this point because that's not going to do anything to the pH of our solution, or it's not going to... Sodium ions don't react with water in any way, which is weird because sodium reacts very violently with water, but Na plus doesn't really do anything in water. So ClO minus, when we add that to H2O, because this molecule overall has a negative charge, again, it's going to pull a positive hydrogen away from the water, okay? And then we're going to end up with HClO plus OH minus. Does that make sense? Those are kind of the two big things that you're really looking for when you're looking at when you're looking for weak bases. Okay, you want to look for either nitrogens, or you want to look for negatively charged compounds. Hang on just a second. All right. Okay, sorry about that. So, solution is made by adding solid sodium hypochlorite to enough water to make 2 liters of solution. If the solution has a pH of 10.5, how many moles of NaClO are added to the water? That's interesting. That's a little bit different than the questions we've been asking at this point. So, first thing we're probably going to do here is write the equation for this reaction, which we just did, okay? But I'm going to write it again because it, never hurts to have an ice table. HClO plus OH minus. Okay. All right. So there's our reaction. Again, the sodium is in there, but we just don't care about it because it's not doing anything in the solution. Okay. It's the ClO minus that's reacting with the water. So we're adding sodium hypochlorite to enough water to make 2 liters of the solution, and it's telling us that the solution has a pH of 10.5. And we want to know how many moles of NaClO were initially added to the water. Okay? So let's think about our ice table here. What do we know on this one? Okay, we can use the pH to find the concentration of the OH minus. And is that going to be the OH minus at equilibrium or initially? Okay, remember, when we have a pH, we're assuming that we have let this thing come to equilibrium before we measure it. Okay, that's just good lab practice to give it some time to equilibrate. I'm not sure if that's a word or not, but I like it. So the pH is 10.5 here. You got to be a little careful because we're trying to find the OH minus concentration, right? So if we 10 this, that's going to give us the H plus concentration. All right. So what we need to do first probably is find the pOH of the solution, what's the pOH of the solution? If the pH is 10.5, the pOH should be 3.5. Good, because they have to add up to 14, okay? So if the pOH is 3.5, then we 10 that's going to give us our OH minus concentration. So 10 to the negative 3.5. Going to give me 3.16 times 10 to the negative fourth. Okay, now our initial OH minus concentration was 0. Okay. We can assume our initial HClO concentration was also 0. I mean, if you want to fill this thing out. So this is going up by 3.16 times 10 to the negative fourth, which means this is also going up by 3.16 times 10 to the negative fourth based on the stoichiometry in our reaction, which is just 1 to 1 to 1 to 1. Which means this is going down by 3.16 times 10 to the negative fourth. Okay? Well, what else do we know here? We know the liters of the solution, okay? That's going to help us maybe at the end because they're asking us for moles. We're missing one piece of information here that might help us. What might help us here? Okay, we are adding solid sodium hypochlorite. I mean, that's important, but it's not going to help us right now. This was kind of tricky. Okay, well, so again, just sort of thought process on this one. If in doubt, make an ice table, okay? If still in doubt, write your equilibrium expression, right? Those are a couple of good things to always do, right? So let's think about this. Kb is equal to, let's see, we got 3.16 times 10 to the negative fourth squared, right? Because we have 2 of those in the product, divided by, well, I don't know yet. So I guess this is x. Is that right? Well, wait a second. What other piece of information might be useful here? Now can you see it? There we go. And we need the Kb for this thing, right? Okay, which, you know, if I was being a good teacher, I would have that up there already. Okay, so for hypochlorite, the Kb is 3.3 times 10 to the negative 7th. Okay. Okay, now we can solve this thing, right? Because now we just have one variable. That's our x, our concentration of the ClO minus at equilibrium. Okay. So solving for x here, we're going to end up taking the 3.16 times 10 to the negative fourth, squaring it, and then dividing that value by 3.3 times 10 to the negative 7th. Right? Is everyone with me on that? Okay, just want to make sure we don't need to go through that in more detail. So what that's telling me is at equilibrium, my x, I can kind of erase this now, is going to be 0.3, how many sig figs here? 2, 0.30. Okay? Well, that's good because now we can figure out our initial concentration just by adding this 3.16 times 10 to the negative fourth to the 0.3, right? Because that'll tell me how much I initially had. Does that make sense? Okay. Now, this is not going to be much different than 0.3. I think with our number of sig figs, it might still be 0.3, actually. Is it? Okay. So, yet again, another example of how in our normal equations here, when we take minus x and we do our plus x and plus x, our simplifying assumption is usually justified, right? In this case, our initial concentration minus our x gives us the same thing for our final concentration. It makes no difference to the number of sig figs that we're measuring things to, okay? So we've got 0.30, that's molarity, right? That's our concentration initially. Okay, what they're asking for is how many moles of NaClO were added. Okay, so now what do we have to do? Right, just use the molarity equals moles over liters equation. Okay, so I should just write the numbers in. 0.30 equals moles over 2 liters, right? So the number of moles is 0.6. Okay. So we had 0.60, running out of room here, moles of the ClO minus to begin with. Or really the NaClO, right? Does everybody understand how those are the same? You got it? Because this is kind of our X, the number of moles here. Okay. Yeah, so if you multiply both sides by 2, that'll get rid of the 2 on the bottom, and then you got 0.6. Okay, now 0.60 moles of ClO minus. I'm being a little bit lazy there, because ClO minus, because this dissociates in a 1-to-1 ratio, that's also the number of moles of NaClO we started with. Okay? That one's tricky. I kind of like that question, though. It's a little bit different, because it gets boring doing the same thing over and over again. A solution of NH3, what's that? Yeah, listen here. A solution of NH3 in water has a pH of 10.5. What's the molarity of the solution? Okay, this actually, yeah, that kind of is what we're doing, isn't it? Doing the same thing again. So I'm going to skip that one, okay? Because this one's telling us a pH of 10.5, so this is the process that we did, right? That's going to get us back to our initial concentration, just like it did on the last one. So the only difference here is in the second question, once you get here, you can stop, because that's all they're asking you for is the initial concentration. Okay. All right. So that they let me talk. They could possibly ask you that question on the AP exam. All right. I swear, on these videos, I'm either hacking or stuttering or same thing. I don't know. Which of the following ionic compounds would be most likely to form a weak base that bubbles when added to an acid? Okay, that's just kind of to make sure that you remember, right? What bubbles when you add it to acid? Right, well, anything that's a carbonate that is going to form CO2, right? So, yep, that's going to be the one that bubbles. Just thought I'd throw that in there, because it is a weak base. Any carbonate is usually going to be a weak base, because as soon as you put it into water, it's going to dissociate, right? So then you're going to end up with Na plus and CO3 2 minus, okay? CO3 2 minus looks like a weak base to me because it's negatively charged, so it can probably pull hydrogen off of water, okay? All right, so that's that. Now, what we want to do here is we want to derive the relationship between Ka and Kb. And in order to do that, we would need to use an acid base or an acid conjugate base pair. Okay, so NH4 plus is our acid, NH3 is our conjugate base. All right, so if we write the Ka expression for the acidic reaction, which this is the acid reaction, right? Does everybody see that? As we're looking at it in the forward direction, okay? These Kas are always written assuming that we're reading from left to right, okay? So our Ka for this first one would be what? Again, we simplified this when we left the water out on this first one. Well, we're going to leave the water out in the equilibrium expression anyway. Just products over reactants, right? So NH3 times H plus over NH4 plus. Okay, there's our Ka for that first reaction there. The second reaction is a base reaction. Okay, so you've got NH3. If that reacts with water, then that's going to form NH4 plus and OH minus. Okay, now I want to make sure you understand that's different than what happens in the reverse direction here, okay? But it's the same chemical, all right? NH3 is the same, you know, obviously the NH3 here is the same as the NH3 here, so we would expect it to behave the same. But if we just put the NH3 into water, then it's going to form NH4 plus and OH minus, okay? And so the Kb for this one is going to be NH4 plus times OH minus over NH3. Okay? Now we need to think back a little bit to our last test. Okay? So on our last test, we talked about how you can add equations together, right? So let's think about this for a second. What would happen if we added these two equations together? Okay? Actually, do I have this on another slide? Oh yeah, okay, good. I was wondering where I was going to put that. So if we add these together, we're just canceling certain things out, right? Okay, so what am I canceling out here? No, not the H2O. NH3, definitely, that's on, both sides, and the NH4 plus, right? So then what we end up with here is H2O in equilibrium with H plus OH minus, right? Okay? Now, when we add two equations together, what do we do to their K's? We multiply them, okay? So Ka times Kb, when we add these together, is going to give us, gosh, I'm going to have to remember what I wrote on the last. NH3 times H plus times NH4 plus. Doing a bad job of remembering this morning. Hopefully you guys have enough room for this on your sheet. Times our Kb expression, which is NH4 plus times OH minus. Over NH3, right? Yeah, NH3. I guess I could just look at the equation rather than being lazy. Okay, when we multiply those two together, what's going to happen? Yep, just like they did in the equation, right? So the NH3 is going to cancel with the NH3 here, the NH4 is going to cancel. And so our Ka times Kb is going to equal H plus times OH minus. Huh. At 25 degrees Celsius, assuming we're at 25 degrees Celsius here, what do H plus times OH minus always equal? 1 times 10 to the negative 14th, which we call a special name for that. Okay. Kw, right? Okay. Kw, which is 1 times 10 to the negative 14th. Okay. That's interesting. So what we just said is if you take Ka times Kb, that's going to equal Kw. That seems like it might be useful at some point. Okay. So Ka times Kb equals 1.0 times 10 to the negative 14th. Okay? So that's going to be a useful relationship. So that's what you end up with here, is this. Okay? Now, if we take the negative log of both sides of this equation, you end up with pKa equals plus pKb equals pKw. Okay? But the pKw, if you take the negative log of 1 times 10 to the negative 14th, it's just 14. Okay? So that could also be useful. You may use that less until we get to buffer solutions, okay? But I'm just mentioning it here that this is also the case, all right? But this is kind of a big one, okay? If they tell you a Kb for an equation, every once in a while in the AP exam, what you really need is the Ka, but that's not a big deal because you can get from the Kb to the Ka as long as you remember this formula, okay? And I'm pretty sure this formula is on your equation sheet. You have to check to make sure, but I think it's there. Okay. So, sample problem here. Calculate the base dissociation constant Kb for the fluoride ion, F minus, and the acid dissociation constant for the ammonium ion. Okay. Here's the thing. The book does not actually give us the base dissociation constant for fluoride. Okay? What the book does give us, and this is the reason that they're asking this question, is because they're assuming you're looking at the K's and the KB's out of the book. It does give us the Ka for HF, hydrofluoric acid is 6.8 times 10 to the negative fourth. Well, how does that help us? Right, this is the HF. This is for HF, right? HF is the conjugate acid of F minus. So everybody see that? So when the F minus takes a hydrogen from water, then it's going to become HF, okay? And we know what the Ka for HF is. So that should allow us to calculate the Kb. All right, so all we have to do here is, remember, Ka times Kb equals 1.0 times 10 to the negative 14. Whoops. That's supposed to be 14. All right, so 6.8 times 10 to the negative fourth times, this is essentially our x, equals 1.0 times 10 to the negative 14. I could have kept that as Kb. I don't know why I rewrote it as x. X is Kb. All right. So then all you have to do is take 1 times 10 to the negative 14th, divide it by 6.8 times 10 to the negative 4th. That's going to give you your Kb. It's going to be equal to 1.47, 1.5, I guess, times 10 to the negative 11th. Okay? And that's for that's for F minus. Okay? And then the acid dissociation constant, Ka, for the ammonium ion, well, guess what? We're not given the acid dissociation constant for ammonium. What do you think we're given in the book? The Kb for hydrogen. What's the conjugate base of NH4+? NH3. Okay? So after it gives away that hydrogen, so what we'd have to do is look up the Kb for NH3. Okay? And Kb for NH3 is, I should label this somehow. Kb for NH3 is equal to, I should remember that because we've talked about it twice already in these notes, but I do not remember it off the top of my head. 1.8 times 10 to the negative fifth. Okay. So then, you probably can see this at this point. All we have to do is take whichever one we know and take 1.0 times 10 to the negative 14th divided by that number, and that'll give us the other one. Okay, so if we're trying to find the Ka here, we just take 1 times 10 to the negative 14th, divide it by 1.8 times 10 to the negative 5th, and then our Ka for NH4 plus is going to be 5.6 times 10 to the negative 10th. Okay? Does that make sense? You guys understand that? It's just plugging into that formula, basically. Ka times Kb equals Kw. The hard part on this, I think, is figuring out what is the conjugate acid or the conjugate base of the one that they're asking us for. Okay? Do I? On this one? Which of the following anions has the Larget's base dissociation constant? Well, I don't know how to answer that question, because I don't know what a Larget's is. I'm assuming I meant largest there. Oh yeah, I just switched the S and the T. Largest base dissociation constant, NO2 minus, PO4 3 minus, or N3 minus. Okay? Alright. So, how would I figure this one out? Is this the last one, by the way? Okay, alright. So we can, now we can talk about this one. You might have a question like this, so we could probably need to talk about it. But we're going to need to know some stuff here. Okay, first of all, NO2 minus, probably going to be a base, right? But we probably don't have the Kb for NO2 minus given to us in the book. I'm guessing that's why they're asking this question. What do you think we could look up fairly easily? If we can't look up the Kb for NO2 minus, what could we look up? Okay, we can look up the Ka for the conjugate acid of NO2 minus, right? What would the conjugate acid of NO2 minus be? HNO2, right? Okay, it's just with a hydrogen on it. Okay, so again, if you're not sure about that, here's how you can do this. Okay, NO2 minus. Remember, these bases are always reacting with water, right? Okay. So then just think about what a base does. A base takes a hydrogen from the water. Okay. So then you're going to end up with HNO2 here plus OH minus. Okay. So if this is your base, this is your conjugate acid. Okay, and this is where that being able to identify the conjugate acid thing kind of comes in handy. All right. So once you know that's a conjugate acid or a base conjugate acid pair, then you can use the Ka times Kb equals Kw equation. Okay, it has to be for conjugate acid base pairs. So this one, again, we probably can find the Ka of that, even though we can't find the Kb of this. All right, and they might do this to you every once in a while in the AP exam, where they'll give you the opposite of the one that you need, right? And then you have to use this equation to figure out the Ka or the Kb for the one that you actually do need. So the HNO2, flipping back and forth between the acids and bases here, the Ka for that one is 4.5 times 10 to the negative fourth. All right. So if that's our Ka, then our Kb for this one would be 1 times 10 to the negative 14th divided by the Ka. That's going to be 2.2 times 10 to the negative 11th. All right. Not a very strong base, right? As we can tell. The conjugate acid is much stronger than the base, which that's going to happen most of the time. I say most of the time. That's going to happen all the time. Okay, if you have a fairly strong conjugate acid, you're going to have a fairly weak conjugate base. It's just the way that it works. Okay, because when you multiply those Kas together, they have to equal 1 times 10 to the negative 14th. Okay, so PO43 minus. Actually, you know, short of calculating all of these, that's actually probably the easiest way to do this, and I wasn't thinking about that till just now. Let's just figure out the Kas for all of the conjugate acids of these things, and then we can compare them, right? So we just said if it has a large Ka, it's going to have a relatively small Kb, all right? So I'm just going to find the Kas of the conjugate acids of all of these things. So the Ka for the this is for the HNO2, okay? What's the conjugate acid of PO43 minus? Okay, yeah, we have to be a little bit careful here. Let's just attach one hydrogen to it, okay? That one's kind of tricky. Where am I here? I need to find my polyprotic numbers. Here we go. Okay, so the conjugate acid for PO43 minus is going to be HPO42 minus, okay? So the Ka for HPO42 minus that I'm finding in the book is let's see here. 4.2 times 10 to the negative 13th. Okay, and then the Ka for the N3 minus, what would be the conjugate base for that? I said conjugate base, I meant conjugate acid, sorry. What would be the conjugate acid for the N3 minus? HN3 or HN3, that's weird. Yeah, I guess that's what it would be. We're used to NH3 rather than HN3. Did I make a mistake there? I made a mistake. That's not N3 minus. That doesn't exist. Sorry. It's N3 minus. Okay, that 3 is also supposed to be a superscript there. All right. Yes. So it should be N3 minus, not N3 minus. Okay. Yeah, that makes a lot more sense. So then, yeah, something about that did not look right. So our Ka for that one, our conjugate acid here would be H in 2 minus, okay? So then we'd have to look that one up and try and figure that out, okay? Yeah, we're running out of time. All right, we might finish talking about this one in class, just to make sure that you guys are understanding that, because I think it's a good one for the conjugate acid-base stuff. All right, we'll see you in class.